To the last day of the conference, and the first talk of today will be the second part of the talk of François about quasi-modularity of Hodge cycles. So thank you, François.
Thanks a lot. So today what I want to do is two things. So first I want to sketch the proof for the main theorems that I said yesterday. So sketch the proof of what I call theorem 2 and theorem 3. So these are quasi-modularity and respectively mixed Mach modularity of the Zariski closures of Noether-Lefschetz cycles in these Shimura type, so O2 comma n period spaces, where you pass to a toroidal compactification. And the second thing I want to do is talk about the Hodge theory of elliptic surfaces and give some applications of these ideas in that world. Okay. So first to sketch this proof, so just to remind everyone the setup, so we have this D mod gamma, which is a K3 type period space for way 2 Hodge structures. And we can take a partial compactification that's toroidal of type 2. So here we're only adding in boundary divisors that correspond to isotropic 2 planes. And then we can pass to the full compactification, which depends on this choice. So this is a choice of fan in this positive cone in the hyperbolic space associated to one of these isotropic lines. So this is C plus inside I perp mod I, real points of that. Okay, so the basic proof strategy for how to understand the closures of the special cycles. The first step is a topological statement. So I want to show that for any test class, so a class in homology in the complementary dimension, we can split it. So we can write mu as mu interior plus mu boundary, where mu interior is a class in H2 of the open period space, D mod gamma, and D boundary is H2 of D mod gamma bar minus D mod gamma. So I'm being a little bit, I'm just using D mod gamma bar to denote either this partial compactification or the full compactification. The structure of the argument will be the same for both. Okay, so that's the step 1. So you can split any homology class. And then step 2 is, well, I want to show this quasi-modularity or Mach modularity. So I'm going to intersect mu with my series, so either with phi 2 of q or with phi 3 sigma of q. And so using the splitting statement, this breaks up into 2 things. So first I have my mu interior dot phi 2 of q, and I have my mu boundary. Intersected with phi 2 of q. And same thing here. Okay, and so then the idea is that this intersection is going to be a modular form using Kudla-Milson. So these parts are going to be modular forms. So this is in mod 2 plus n over 2 by Kudla-Milson. The theorem 1, I guess this was theorem 1 from yesterday. And the point is that this is a compact 2-cycle, and we're intersecting it with a non-compact codimension 2-cycle, but that's OK. As long as one of them is compact, there's still a well-defined intersection product, and so we just use the modularity of this series valued in H upper 2. OK. So there's nothing new there. And then the key point is that we need to compute these parts. And so here we better get a quasi-modular or mock modular form. And the point is that you can compute these directly by working entirely inside the boundary divisors. Okay, so how does that go? So in the type 2 case, type 2, so the type 2 boundary divisors they don't touch each other. So it's a disjoint union of smooth, irreducible divisors, delta j. And each delta j is isomorphic to the lattice j perp mod j. So this is a negative definite lattice tensored over Z with the universal elliptic curve. And then you quotient by a finite group, which is just the action of the stabilizer group of J inside gamma. So don't worry too much about this finite group. Since we're working over rational cohomology, it's not really going to matter. The point is that, so what is this? This is like the self-fibered product R times of the universal elliptic curve over H mod SL2Z or something, finite index in SL2Z. Okay, so that's what this is. And so then the question is, so to compute this term, I need to know what are the limits of all the Noether-Lefschetz divisors in this divisor. So the limits of CD, so i.e. if I take the Zariski closure CD bar and intersect with delta J, what do I get? And it's maybe not surprising that what I get is I just take the union over all vectors V in J perp mod J, such that V squared is equal to minus 2D of just V perp tensor E. Okay, so this is the kind of limit Hodge theory computation that needs to happen. So this is exactly how these CDs crash into the boundary divisor delta J. Okay, and so this intersection product of this homology class supported in delta J intersected with these guys can then just be computed inside this family of abelian varieties. So when you compute, this intersection product, you're going to get the sum over all V in J perp mod J of Q to the V paired with V over 2 and some kind of quadratic weighting factor. So quadratic function of V as the weighted factor. And this is what we call a weighted theta function. So if you didn't have this weighting function, it would just be the sum of Q to the V squared over 2, which is just a standard lattice theta function. And when you add in this weight, it's actually a quasi-modular form. So this is the construction. Quasi-modular form. And it turns out that if you compute the weight, it's the correct weight. It's the same weight as the interior contribution. That's kind of a nice thing. So say again?
This is just the part E2 times modular form.
Yeah, that's what quasi-modular form is, yeah. Yeah.
Degree 1 in E2.
That's right, exactly, yeah. Yeah, so you can, for example, you can take the Q derivative of this theta function, and then you would be weighting it by V dot V over 2. But you could also weight by other quadratic factors, and it's still a quasi-modular form.
But it's not degree 1, because that it is a polynomial of E2. The degree is 1?
Yeah, the polynomial, the polynomial is degree 1 in E2. So it's like E2 times some polynomial in E4 and E6. Yeah. How do you see that it's like that? I see, yeah. So maybe I should be a little more specific. You're saying why is it like that? Yeah, the idea of the proof is, it's a classical fact that if you use a harmonic polynomial to weight, then it's still a modular form. And I can write any quadratic weight as something harmonic plus just QDDQ of this theta function. So. So a similar kind of thing in type 3. So we have to do first I have to tell you kind of what the boundary divisor looks like. So the boundary divisor now is labeled by an isotropic line I and a ray in this cone. So now I'm fixing a ray, which I call C, inside this positive cone. And so each of these divisors is a toric variety. And it's a compactification of, if you like, I perp mod I tensor over Z with C star. So right, this is the toric. This is just C star to some power, and I'm taking some toric variety that compactifies that, which toric variety I take is just dictated by the fan that you get by just looking at the star around that particular ray in the positive cone. Okay, and so kind of similar computation then of what is the limit of CD bar? Well, it's going to be the exact same formula, so I won't write it again, but it's just the union over V of V perp, but now V perp taken in this space. And so the answer of the series then is a sum over V in I perp mod I now of Q to the VV over 2. But now you have a more complicated weighting function. So this is now a piecewise linear function of V. So the weight function is, like I said, piecewise linear and is compactly supported if I look in the projectivization of I perp mod I over R. So it's a little exercise to see that this actually converges, that this piecewise linear function, because there's an infinite number of vectors in this hyperbolic lattice of a given norm. So you have to be a little bit careful. If we didn't have any kind of weighting factor here, then this would not converge, because you'd be adding up the same q to the same power infinitely many times. This is just a hyperbolic lattice. So you have to check that this converges, and then you have to check that this is a mixed Mach modular form. And so for that, so we use a criterion of Vinieras from the 90s, I think, which says, so which weight functions give harmonic mass forms. So which weighted theta functions give harmonic mass forms. And the definition of a mixed Mach modular form is the holomorphic part of one of these harmonic mass forms. So we also need to do this completion construction. So complete the weight function to some smooth. You have to kind of smooth it out. So we smooth out this piecewise linear function, and then use the criterion of Vignales to see that that the resulting thing is a harmonic mass form, and this is the holomorphic part of the harmonic mass form. Okay. So maybe that's all I'll say about that part of the proof. But I want to go back to step one, that sort of topological part. So this is the splitting theorem. For H2 of d mod gamma bar. So in general, if you want to do a splitting like this with respect to a smooth irreducible divisor, let's say, then the first thing you would do is write down Meyer-Vittoris sequence for the covering of your compactification by a small neighborhood of the boundary divisor and by the interior. So you have H2 of the interior, direct sum H2 of, I'll just call it the boundary, mapping to H2 of d mod gamma bar. And then the next term is going to be H1 of the punctured normal bundle. So just take the neighborhood of the boundary and then just remove the zero section. So this is the sort of intersection of the two open sets in Meyer-Vittoris. And what we want to show is that this is surjective. Right, that's how you'd get a splitting. And to do that, that's equivalent to showing that the next map here, it would be injective. H1 of the boundary. Okay, and so this thing is often zero, at least rationally. So I'm going to ignore this one. It doesn't really help us to try to study injectivity of that one, but it would be enough to show injectivity of the map from H1 here to H1 of delta. And this is actually just a map inside some Giesen sequence. So the punctured normal bundle of a divisor retracts onto a circle bundle. So you can study that map using the Giesen sequence for just this S1 bundle over the boundary. And so what does that sequence look like? So yeah, the map that we're interested in is H1 of the circle bundle, pushing forward to H1 of the base. And the previous map is H0 of the base, and then H2 of the base. Right, where this previous map is just the Euler class of the C star bundle associated to this circle bundle. So again, if we want to show that this thing is injective, it suffices to show that this thing is surjective. Okay. But this is just cupping with some class in H upper 2. And it's valued in H lower 0 of delta, which is just Q. So in order to show surjectivity, you just need to show that it's non-zero. And that's the same as just showing that the normal bundle of the boundary divisor is non-trivial. So it's a very sort of simple condition. And this works very generally. I mean, anytime you have a smooth projective variety with a boundary divisor, if this smooth divisor has a non-trivial normal bundle, then you're going to have this splitting statement. Okay, and sure enough, delta has non-trivial normal bundle. Let's say delta J in type 2. And I mean, one reason for this is that it's actually the exceptional divisor for the blowdown to the Bailey-Borel compactification. So if you remember, we kind of defined the toroidal compactification as a blowup of this singular projective variety. And any exceptional divisor of a blowup automatically is going to have non-trivial normal bundle. Okay. And so then just like a remark, if we try to do this for the higher codimension special cycles or higher dimensional test cycles mu, so mu now in H2R of d mod gamma. You would do a similar thing, but you would have to use a little bit more machinery. So instead of H2 to H0 here, it would be some higher thing, some higher dimensional, even homology. And so there you need to use hard Lefschetz. And the degeneration of Leray spectral sequence for smooth projective morphism. Okay, but this is a little bit deceptively easy because these delta J's are smooth, irreducible boundary divisors. And what we really need for our theorem is to show a splitting statement for the full boundary of the toroidal compactification. So next I have to tell you, if instead of just a single smooth, irreducible boundary divisor, you have a union, let's say, over C of delta IC. So this is sort of one clump of type 3 boundary divisors that occurs over the type 3 stratum of Bailey-Borel. So this is the kind of lying over point sub I. In the Bailey-Borel compactification. So I think this is also kind of an interesting general situation. You know, is it true that you can split relative to some simple normal crossings boundary divisor, say inside mg bar or inside any of these toroidal compactifications? And the answer is actually kind of subtle. So you write down the same long exact sequence here, so this Meyer-Vittorius sequence. But now you have a punctured normal bundle of a simple normal crossings divisor, which is actually not a circle bundle anymore. It's some kind of plumbing of circle bundles. And so to analyze that, in our situation, we use what's called the toric moment map. So I'll just give a simpler example of this kind of setup. So just consider P2, CP2 with the boundary divisor, which is just the 3 lines in P2. And you want to know, can you describe, so what is the normal bundle of the boundary? So here the boundary is just the union of those 3 P1s. Okay, so how do you understand this? Well, so the point is that there's this moment map, which is not an algebraic variety type of thing. It's a symplectic geometry construction. There's a moment map which expresses your P2 generically as a torus bundle over the polytope associated to the toric variety. So in this case, the polytope would just be this triangle. And the fiber over an interior point is a T2. The fiber over a generic boundary point of the polytope is a T1. And the fiber over the corner is just a point. Okay, and so in this picture, you can kind of see explicitly what the boundary is. If you took the union of the 3 sort of edges of that triangle, then the preimage then is going to be the 3 P1s. Inside your P2. And so to understand the punctured normal bundle, I just need to choose some slightly smaller triangle inside of that triangle. And then you see that actually this normal bundle is diffeomorphic to T2 times S1, or just T3. Okay, so it's very much, it's just a trivial thing. Even though the sort of complex normal bundles of each of these lines is a non-trivial line bundle. So you have O of 1, O of 1, O of 1 as the normal bundles to the individual components. But if you take them all together and you compute the punctured normal bundle, you get something trivial. So just having non-trivial normal bundle on each component is somehow not enough when you're trying to do a splitting with respect to a simple normal crossings boundary. Okay. Okay, but we can still do this computation. So the way we do this is we express, so n delta I punctured turns out to just be an n-dimensional torus. across the hyperbolic space, mod the stabilizer of I inside our arithmetic group gamma. And then the structure mapped down to delta I. This ends up being this infinite type toric variety where you actually just build a toric variety over the entire positive cone, and then again quotient by the stabilizer I. Okay, and so to check the injectivity that you need, check injectivity on H2. We again have to use a spectral sequence, so we use the Leray-Cartan spectral sequence. Which computes cohomology of a quotient space by a discrete group in terms of the group cohomologies of the cohomologies of the universal cover. So I'd like to pose a question that I think is sort of interesting. I don't know how to prove it, but I sort of believe it at this point. Is if you have suppose you have a variety y and a simple normal crossings divisor delta. So this is if you want, this is like a smooth log pair. And assume that there exists some contraction y delta to y bar z, where delta is getting contracted to something of dimension much smaller. So dimension of z is small. Then does there exist a splitting theorem like this? On H2 of y. On y, I guess I just mean y as the smooth projective thing. But yeah, y bar, yeah, sure. I see what you're saying, sorry. No, on y, yeah. So I think this is true if this bottom space is smooth. But if this bottom space is singular, I don't know how to prove it. And that's the situation that we're in here, because in our situation, this y bar is the Satake-Bailey-Borel compactification, and this y is the toroidal compactification. So it's also not hard to prove that if this is an irreducible divisor with one component, then it's true. That's just sort of, from what I said before, the non-triviality of the normal bundle for an exceptional divisor. Okay, so that wraps up the first part of the talk. Now I want to sort of move on to a different topic, which is elliptic surfaces. So maybe, first of all, are there any questions about the proof of the theorem? No, I mean, this is just sort of shorthand. It just means a smooth projective variety with a simple normal crossings divisor. That's all I mean.
Once you mentioned the Kaplan suite, they put also locus structure and all these compactifications.
I don't, but probably one should. Yeah, I think. Ultimately, I'd like to have a splitting theorem for the Kato-Usui compactifications too. And at this point, I can only do it for some partial compactification. Again, where we're just sort of taking advantage of this irreducible statement. But if you want the full sort of simple normal crossings thing, I don't know how to do it without using all these spectral sequences, which I think are not maybe an essential thing. I think it's sort of an accident in this particular situation that you can use those. So a lot of this conference was talking about Hodge theory of hypersurfaces in projective space. And that's certainly an important example. But I also want to kind of highlight elliptic surfaces because they're also very nice from the perspective of Hodge theory. And you can say a lot and a lot is known. You can also kind of formulate a lot of it in terms of weighted hypersurfaces, at least in the case of genus 0 elliptic surfaces, which is what I'll explain. So when you have an elliptic surface, there's a few basic discrete data you can associate. So an elliptic surface for me is going to be a smooth projective algebraic surface with a structure map down to a curve. And so you have the genus of the base curve. And then you have the degree of the Hodge bundle. So the degree of lambda, I'll call D. So lambda, you can think of it in different ways. You can think of lambda as the push forward of the relative dualizing sheaf. Maybe that's the easiest way. But essentially, it's like if you just uniformize all the fibers, it's what is the line bundle that you're getting over the base. Okay. And it's a basic fact that this D is always greater than 0 if your elliptic surface is non-trivial. As long as it's not just a product of the base curve with a fixed elliptic curve, then the degree that you're getting here is positive. So let me call this space F, G, comma, D. So let's say that's the moduli space of these elliptic surfaces. So a nice way to construct this, you can kind of construct this moduli space using geometric invariant theory. And there's an explicit parameterization. So how do you make an elliptic surface? So first you need to choose your base curve, choose your Hodge line bundle, L, of degree D. And then I need to choose my Weierstrass coefficients. So I'm going to choose a polynomial A, which is a global section of L to the 4th power, and B, which is a global section of L to the 6th power. Okay, so if I choose all this data, I can form a surface y squared equals x cubed plus ax plus b, which is inside some kind of projective bundle. So it's inside a certain P2 bundle with the correct weights over C.
Sorry, B is a global section as well?
Yeah, sorry. All right, and then I need to quotient, quotient this parameter space by automorphism group of C. So this is only going to be relevant if the genus is 0 or 1, and also by the action of C star, where the C star action is T dot AB is T squared A, T squared B. Okay, so let's just count dimensions. So the dimension of FGD is, first of all, that you need to choose the curve, so it's the dimension of MG, plus you need to choose the line bundle, and there's a G-dimensional Picard group of a smooth curve. Then I need to choose H0. There's a vector space L to the 4 and a vector space L to the 6. And then I need to subtract 1. Right? So you get 3G minus 3 plus G plus 4D plus 1 minus G plus 6D plus 1 minus G minus 1. This is going to be important, I promise. So the final answer then is 2G minus 2 plus 10D as the dimension of this moduli space. Then you can also compute the Hodge diamond without too much problem. So H1 of the elliptic surface, as long as it's non-trivial, is isomorphic to H1 of the base curve. So I won't write that. So H1 is just 2G dimensional. And then, but H2, the interesting part, has Hodge decomposition of type G plus D minus 1, 2G minus 2 plus 10D in the middle, and G plus D minus 1 on the ends. Okay. And then it's sort of standard to pass to what we call the primitive cohomology, where I'm going to remove the two algebraic curve classes which are always present. So you always have the elliptic fiber class, and you always have the zero section class. So when I say elliptic fibration, elliptic surface, I mean with a section always. which is why you can say that it has a group structure. It's an elliptic curve in every fiber. So there's sort of these two automatic classes that are always there. So when I say H2 prim, I mean the complement of those two classes. So you need to take away 2 from the middle. Right? Excuse me, actually, yeah. This was 2g before, and now it's 2g minus 2. Okay, so we have the period map for this situation goes from FGD to D mod gamma, and then goes to one of these locally symmetric spaces, positive definite Grassmannian mod gamma. Let me just write that. So the dimension over R of this is twice G plus D minus 1 times 10D plus 2G minus 2. The fibers of this map are O2P mod UP, which has the real dimension P times P minus 1. So what this means then is that if G plus D minus 1 is equal to 0, then the period map is trivial. So then the period map just maps to a point. If G plus D minus 1 is equal to 1, then these have the same dimension. So then dimension of FGD is equal to the dimension of D mod gamma, which is also equal to the dimension of this locally symmetric space. And when G plus D minus 1 is equal to 2, then the dimension of FGD is 1 less than half of the dimension of D mod gamma. And in the Griffiths transversality condition then corresponds to a holomorphic contact structure on this space. And the image of the period map is a complex Legendrian manifold locally inside D mod gamma. Okay. So let me, for now, restrict to G equals 0 and say sort of some interesting things that are known. So the first theorem is by Cox from 1990. I feel like all the theorems I'm citing are from 90, which is the year I was born. So Cox says that all Noether-Lefschetz loci in F0D are typical. And they correspond to jumping Mordell-Weil group, so the existence of an extra section. There's also a theorem by Miranda. Saying that if we allow mild singularities, if we allow ADE singularities, in our surfaces, in the elliptic surfaces in the moduli space. First of all, they still have pure Hodge structures, so they have pure Hodge structures. And we do get atypical components. So we get atypical Noether-Lefschetz loci in codimension n. where n is the subscript on A, D, or E. So if you have an AN singularity, that corresponds to a codimension n locus in the moduli space of elliptic surfaces that has a special Hodge structure. And so this is going to be this is going to be an algebraic locus, right? The sort of ADE singular guys. But then this is going to be an infinite union of sort of typical components. So now I want to talk a little bit about infinitesimal Torelli, so what's known. So theorem by Saito, and then later there was a mistake corrected by Kloosterman. And it says that as long as GD is not equal to 0, 1, or 1, 1, then S satisfies infinitesimal Torelli if the J map is non-constant. Okay, so the J map is just, you have your A and your B, you take 4A cubed plus 27B squared. This is a section of L to the 12th power. And it defines for you a map to P1, just the J invariant of the fibers. So having constant J map is a very special condition. So it gives you a very small sublocus inside FGD. So the statement just is, this is basically kind of an aside. As long as the J map is not kind of degenerate in that way, then it always satisfies infinitesimal Torelli. Not always, actually. You can actually get, you can do like, if A equals 0, then you get an isotrivial fibration that still has non-trivial Hodge bundle. It's interesting, like computation. Okay, and originally Saito's paper had proved this statement also for 1, 1, but Ikeda showed that it's false, actually. There are examples, so there exist surfaces S inside F1, 1, such that infinitesimal Torelli fails, and the J map is non-constant. Okay, and so the theorem I want to say is sort of resolving this situation, so explaining what exactly happens for this 1, 1 case. So this is a recent preprint that just came out. We put it up a few weeks ago. So it's with Phil Engel and Abigail Ward. And what it says is that the period map is dominant in this case. So the period map, which goes from F11 to D mod gamma, is dominant. So in particular, infinitesimal Torelli, so derivative being injective or being isomorphism is true most of the time. So holds generically on F11. Because these have the same dimension. So these both have dimension 10. And we also show that the degree of the period map is greater than 1. We expect that the period map has degree 2, but we can't prove that right now. So the proof of this, to sketch, it's very geometric. It involves a degeneration to the boundary, degeneration to the type 2 boundary, so the boundary delta J. I'm writing this because there's actually a unique divisor component of type 2 in the toroidal compactification of this particular d mod gamma. So this d mod J inside of, delta J inside d mod gamma, take any toroidal compactification. And so geometrically what we're doing is, so we start with an elliptic. One of these surfaces, I call them elliptic surfaces. So they're elliptic surfaces over an elliptic curve. There's a distinguished section, as I said, and then there's also a distinguished fiber because the Hodge bundle of this elliptic surface is degree 1. So it's isomorphic to O of P for some particular point in the base. So you have each of these elliptic surfaces comes with these two elliptic curves kind of baked into its definition. And so you can degenerate it to where the base becomes just a nodal rational curve. And then the surface then has a self-crossing kind of thing. So it's self-crossing along some smooth elliptic curve. And the normalization of this non-normal surface up here, this is just a rational elliptic surface over P1. So that's the sort of simplest, this is the normalization map. The simplest example of one of these elliptic surfaces, so that's an element of F01. So if you're keeping track of numerics, this has 12 singular fibers. The original guy also had 12 singular fibers. That's essentially because the Hodge bundle had degree 1. You can compute the discriminant just from those A and B. So this has 12 singular fibers, so it's an element of F01. So rational elliptic surface, and this is an element of F11. Okay, and so then we show that the sort of mixed period map that goes from these sort of non-normal singular surfaces to the boundary delta J is dominant using the geometry of plane curves. So each of these rational elliptic surfaces is actually just the total space of a pencil of 2 cubics in P2. And if you specialize to very special cubic pencils, you can show that there's only one point with period 0. So the mixed periods are just, so the mixed period is encoded by, this is kind of what Emre was saying in his talk, is encoded just by a homomorphism from H2 of the normalization to the Jacobian of the elliptic curve along which you're gluing. So it's just the restriction morphism from that normalization to the two curves that you're gluing. So there's sort of two copies of E which are being identified in this normalization, and then this is the mixed period of the singular surface. It's just given by that homomorphism. Okay, and then once you have this dominance at the boundary, you can show that any of these singular surfaces actually can be smoothed. So that's a pretty standard calculation that you can always smooth this self-normal crossing elliptic surface to one of these smooth elliptic surfaces, and so you get the full theorem that way. I'll just say one short thing about, so that's how you show dominance. To show that the degree of the period map is bigger than 1, we take a different degeneration. So you can also degenerate in such a way that the fibers all become singular. So to a surface where the general fiber is a nodal elliptic curve now, and the base remains smooth. And the way the equations work, you have exactly 2 cuspidal fibers, and the rest of the fibers are nodal. And so this is, again, a non-normal surface, and if you normalize it, you get a P1 bundle. So this is projectivization of the Hodge bundle plus O. So this is just a ruled surface, again, over that same smooth base. And there's a genus 2 curve, which is a bisection. And you need to glue the 2 different branches of this double cover together in order to get that non-normal surface. Okay. So this is kind of like degenerating the base, and this is like degenerating the fiber. And the mixed period of this one, so the mixed period, sorry? Yeah. So this is just it's the preimage of the singular locus under the normalization map. So there's 2, each fiber has 2 points that are being identified, and so those are the 2 points here. And there are exactly 2 cuspidal fibers, which correspond to gluing a point to itself, kind of, right? And then you can compute from Riemann-Hurwitz formula that if you have a double cover of a genus 1 curve branched at 2 points, it has to have genus 2. So the mixed period here is valued in the prim. So the quotient of this genus 2 curve, so I'll call this curve D. So the prim of D mapping down to C. Okay, and then so it's a very kind of similar argument to that other one. And so we could have also proved dominance this way. And then let me just kind of formulate an interesting conjecture, which is that, so if our earlier conjecture is true, in other words, the period map is degree 2, then there's a birational involution on the moduli space. Involution on F11. So, right, just interchanging the two sheets of the period map. So just sending a surface to another surface which has the same period. And our conjecture is that this interchanges the 2 elliptic curves. So sending kind of an elliptic surface where you have maybe E1 and E2 to some other elliptic surface where you have E2 and E1 as the kind of canonical fiber and section, respectively. And that certainly seems to be the case if you look at the boundary of this toroidal compactification. So now I want to point, let's see. Okay, I have basically 1 minute. So let me point out one more thing, which is that the D mod gamma that shows up here for F11, this 10-dimensional Hermitian symmetric D mod gamma, this is also isomorphic to the moduli of elliptic K3 surfaces with an E8 fiber. So in other words, just polarized by the hyperbolic plane, direct sum E8. In the notation of Adrian's talk yesterday. So in other words, and it's literally exactly the same. The lattice is the same, so the gamma is the same and everything. So we have, in other words, we have 2 period maps. So we have a moduli of K3s, some kind of moduli of K3s, and we have this F11, both mapping to the same D mod gamma. We expect this is degree 2. We know this is an isomorphism. And so the natural question then is, how do I build an elliptic surface of higher genus out of a K3 surface. Like what is this? If you believe the Hodge conjecture, then there should be some geometric correspondence between these two. And you can do this much more generally. So if you kind of keep track of all the different moduli of elliptic surfaces in terms of their genus and the Hodge bundle degree, like I said, the degree has to be positive. So we start here. So this one would be the rational elliptic surfaces. This one would be the K3 surfaces. This is this new class of elliptic surfaces. And this is the class of condo surfaces. And so if you just keep track of the Hodge numbers, you notice that if you look along these diagonals, they have the same PG, so the same kind of dimension on the edge of the Hodge diamond. And if you impose an E8 singularity every time you move up and to the left, you actually get the exact same period domain for these different classes of surfaces. So I conjecture that all of these classes where you impose the correct number of E8 fibers have the same period image. And then the question is, what is the sort of correspondence that must exist from the Hodge conjecture between these totally different looking surfaces? So they're surfaces with completely different genus on the base and different degree of the Hodge bundle. But sort of, yeah, you expect there's some magical way of sort of matching those up. So thanks for listening.
Okay. Are there any questions?